I recommend setting the video viewer quality to HD or the highest setting possible. Otherwise, the text and graphics might be blurry. If the original video is not HD, you'll be restricted to viewing the video at some lower quality. But if the original video was uploaded in HD, you should have the option to set the video viewer to HD. It doesn't hurt to double check that the video quality is set to the highest quality possible. For example, let's look at this video on YouTube. To set the video quality in YouTube, go to the lower right corner and click on the gear icon, which is the settings icon. Then click on quality, then click on 1080p HD. Some video viewers automatically set the quality to a low setting so that the video won't be choppy, but the trade-off is that it can be blurry. Since most of the chemistry lectures will use standstill text and diagrams, it is unlikely the HD setting will result in the video being choppy even in HD. So I recommend setting the video viewer quality to HD or to the highest setting possible, because it's more important that the text and diagrams are clear. Alright, let's start section 1.6 in the OpenStax Chemistry 2E book, Mathematical Treatment of Measurement Results. Learning objectives. By the end of this section, you will be able to explain the dimensional analysis factor label approach to mathematical calculations involving quantities. Use dimensional analysis to carry out unit conversions for a given property and computations involving two or more properties. It is often the case that a quantity of interest may not be easy or even possible to measure directly, but instead must be calculated from other directly measured properties and appropriate mathematical relationships. For example, consider measuring the average speed of an athlete running sprints. This is typically accomplished by measuring the time required for the athlete to run from the starting line to the finish line and the distance between the two lines, and then computing the speed from the equation that relates to these properties. And there is the equation there. Speed equals distance divided by time. An Olympic quality sprinter can run 100 meters in approximately 10 seconds, corresponding to an average speed of 10 meters per second, or 100 meters divided by 10 seconds. Note that this simple arithmetic involves dividing the numbers of each measured quantity to yield the number of the computed quantity. 100 divided by 10 equals 10. And likewise dividing the units of each measured quantity to yield the unit of the compound quantity. That is, meters per second equals meters per second, or meters divided by seconds equals meters per second. Now, consider using this same relation to predict the time required for a person running at this speed to travel a distance of 25 meters. The same relation among the three properties is used, but in this case the two quantities provided are a speed 10 meters per second and a distance 25 meters. To yield the sought property, time, the equation must be arranged appropriately. Time equals distance divided by speed. The time can be computed as 25 meters divided by 10 meters per second equals 2.5 seconds. Just to clarify, this is meters per second in the denominator. Since seconds is in the denominator here, and yet this whole quantity is in the denominator of all of this, you get 2.5 seconds. We can review that if that's confusing. Hopefully you'll be comfortable with this as you work with it. Again, arithmetic on the numbers 25 divided by 10 equals 2.5 was accompanied by the same arithmetic on the units, that is meters divided by seconds equals seconds, to yield the number and unit of the result, 2.5 seconds. Note that just as for numbers, when a unit is divided by an identical unit, in this case meters divided by meters, the result is 1, or as commonly phrased, the units cancel. These calculations are examples of a versatile mathematical approach known as dimensional analysis, or the factor label method. Dimensional analysis is based on the premise the units of the quantities must be subjected to the same mathematical operations as their associated numbers. This method can be applied to computations ranging from simple unit conversions to more complex multi-step calculations involving several different quantities. Now, for the uninitiated, this may seem kind of thick, but as you work with it, it starts to not get so bad. And so the exercises are going to be, there'll be like 40 exercises, because I think the authors recognize that this really does take a lot of practice to feel comfortable with these mathematical operations. And let me just review this here. Okay, time equals distance times speed. Distance divided by speed. Okay, so I will tell you this. It is sometimes difficult translating a word problem into the math. Once you get it into the math, it should be, if you've done it right, it should be straightforward. If the math doesn't work, then maybe the translation from the word problem to the math might not be correct. So sometimes you just have to play with it, and you try to use a little bit of sense. Again, practice will help clarify this. As one organic chemistry professor said, trying to learn some aspects of chemistry is by just reading is like trying to learn how to ride a bicycle by just reading a book. You have to actually do it. And so one thing we're going to try to do is actually go through the exercises, and it would be great if you could do some of the exercises on your own to get practice. So, conversion factors in dimensional analysis. A ratio of two equivalent quantities expressed with different measurement units can be used as a unit conversion factor. For example, the lengths of 2.54 centimeters and 1 inch are equivalent by definition, and so a unit conversion factor may be derived from the ratio. So 2.5 centimeters divided by 1 inch, 2.54 centimeters equals 1 inch, or 2.54 centimeters per inch. I don't like that notation. Anyway, let's just go with it. I've never seen that notation before, but I think you can intuition. This is a conversion factor, converting from centimeters to converting from inches to centimeters. I'm sorry, converting from inches to centimeters. So if you wanted to convert from inches to centimeters, we use a conversion factor like this, and you'll see how these conversion factors work, or how you're able to synthesize them. Several other commonly used conversion factors are given in table 1.6. So 1 meter equals 1.0936 yards. 1 inch equals 2.54 centimeters, and that's exact, which is great. And then we have these others. I'm not going to go into them. There is this one, I don't know how to pronounce it, this one for mass, 1 ounce, and it's of avoirdupois ounces equals 28.349 grams. That always confused me, the different kinds of ounces. And then there's the troy ounce. 1 troy ounce equals 31.103 grams. That's interesting. There are different definitions of ounces in terms of weight. Anyway, we'll just move forward. We probably will revisit this table anyway, so no sense in me just reading it. Besides, it'll put me and you to sleep if I just read through this table. When a quantity such as distance in inches is multiplied by an appropriate unit conversion factor, the quantity is converted to an equivalent value with different units, such as distance in centimeters. For example, a basketball player's vertical jump of 34 inches can be converted to centimeters by using a conversion factor. And I wish they didn't do it quite this way. We can work through the example. So the jump is 34 inches, and you multiply it by the conversion factor, and you get 86 centimeters. Notice the units, inches, cancel, and you get 2.54, and you multiply by 2.54 centimeters, you get 86 centimeters. So 34 inches is equal to 86 centimeters. Since this simple arithmetic involves quantities, the premise of dimensional analysis requires that we multiply both numbers and units. The numbers of these two quantities are multiplied to yield the number of the product quantity, 86, whereas the units are multiplied to yield centimeters. It says inches times centimeters divided by inches, which is centimeters. I'm just going to complain a little bit about the notation. When we get to the exercises, hopefully this will be clear. And in some respects, this is one of the lectures. It's almost better just to do the exercises to see it a little bit better, and then to go back to the lecture. Just as for numbers, a ratio of identical units is also numerically equal to 1, inches divided by inches equals 1, and the unit product thus simplifies to centimeters. When identical units divide to yield a factor of 1, they are said to cancel, quote unquote. Dimensional analysis may be used to confirm the proper application of unit conversion factors as demonstrated in the following example. So let's look at example 1.8. Using a unit conversion factor. The mass of a competition frisbee is 125 grams. Convert its mass to ounces using the unit conversion factor derived from the relationship that 1 ounce equals 28.349 grams. Solution. Given the conversion factor, the mass in ounces may be derived using an equation similar to the one used for converting length from inches to centimeters. X ounces equals 125 grams times the unit conversion factor. Oh boy, I don't like that either. Anyway, the unit conversion factor may be represented as 1 ounce per 28.349 grams and 28.349 grams per 1 ounce. The correct, okay, so that's one thing to point out. You can make two different kinds of conversion factors with 1 ounce and 28.349 grams. The trick is choosing which conversion factor to use, and this is what they're going to cover. The correct unit conversion factor is the ratio that cancels the units of grams and leaves ounces. So if the desired quantity is to be expressed in ounces, this is the way to check. Okay, so I'm going to emphasize again, this is going to be easier if you actually work through the problems and just play with it a little bit. Trying to learn things in the abstract can be challenging. Okay, so let's check your learning. Convert the volume of 9.345 quarts to liters. The answer is 8.44 liters. Okay, I'm going to have to walk through this myself. So let me bring out my slideshow here. Sorry, that was a leftover screen. And I'm going to just do this in PowerPoint. So we're going to try to check our learning. Convert a volume of 9.345 quarts to liters. So let's try that. So the first thing is, let's just look at table. Well, maybe we'll cheat here. Okay, they won't let us cheat. We'll have to do this the hard way. So we have 1 quart equals 0.94635 liters, and 1 liter equals 1.0567 quarts. Now there's a little trick here. I'm going to just point this out. I'm going to give the answer first, and then I'm going to explain it. So let me insert text. Oh boy, apologies to the viewers here. I'm actually learning how to do this in PowerPoint better. So there is an equation feature here. There's an equation feature here I want to use, and to do that, let me pin this and do insert symbol equation. Boy, it's been a while since I've done this. Let me pause the recording and I'm going to try to figure this out. Okay, I'm back. I'm sorry for the little bit of delay as I fumbled through this. I took the liberty while I paused the recording to construct something for the benefit of the viewers. With these conversion factors, I want to point something out. We can make a conversion factor if, for example, we wanted to convert quarts to liters. I'll show you how to construct that conversion factor. What you want to do is take you put in the numerator the unit that you want to end up with, and the denominator the unit you want to get rid of. So if you want to convert from liters to quarts, from quarts to liters, you put liters in the numerator and quarts in the denominator. Now what's interesting is you could see that they've listed two relationships here. 1 liter equals 1.0567 quarts, and 1 quart equals 0.94635 liters. It turns out you could use either quantity, you'll get the same result, provided you put the right units in the numerator and denominator. So for starters, we could take 1 liter, put that in the denominator, and then put 1.0567 quarts in the denominator. Put 1 liter in the numerator, put 1 liter in the numerator and 1.0567 quarts in the denominator. Or you could, in this case, put 1 quart in the denominator and put 0.94635 liters in the numerator. Now if we wanted to do the opposite, and that is convert liters to quarts, we would follow a similar procedure, just kind of reverse the denominator and numerator. Okay, so now let's look at the what the assignment was. Convert the volume of 9.345 quarts to liters. So we want to convert quarts to liters. So 9.345. That's our conversion factor. Now I'm going to put in a new slide. So what I had to do is I had to pause the recording a little bit and then just do some quick write-up on my virtual chalkboard, so to speak, which is really a PowerPoint slide. So let me explain what we're trying to do. We're trying to convert a volume of 9.345 quarts to liters, and there's two ways to do it. You saw earlier that we had these conversion factors. We could use, if we're going to convert from quarts to liters, we want to have the conversion factor that has quarts in the denominator. I pointed out earlier that you can construct the conversion factor two ways to do it. You can pick either one, it'll work, and I'm going to show that here. So we're going to pick the conversion factor that's one of the conversion factors. We'll actually use both that are highlighted in the yellow box. So we can pick a conversion factor that is this one, or we could pick this one. You'll get the same result. And so you can multiply 9.345 quarts by this conversion factor. What ends up happening is, let's see if I can do this. Let's see, insert. There's a way to do shapes. I'll use red to indicate that I want it to be blanked out. So, and let me increase the weight. So the quarts will cancel, and your one should be left with liters. Apologies, I needed to put in liters here. 8.44 liters. See how that cancels out? So a quart divided by a quart equals 1, and so that cancels out. And the final result is expressed in liters. Now let me point out something a little cute here. So if I'm entering this on a spreadsheet, and I encourage people to learn how to do this on spreadsheets, use their computers to do this, and also to even help you round things off properly. So what I did to do this multiplication here, I do 9.345 times 0.94635, and to do that I put a plus in this in cell C2, and I just move the cursor over here to 9.345. I press a slash and then highlight 0.94635, and then I get a number. Hang on, I'm sorry, I multiply, sorry, not a slash, I use a star, and then I get this number, which isn't exactly the number that you see here. Remember the rules for significant digits. You take, when you're doing a multiplication, you take the number with the fewest number of significant digits, and that number, the number of significant digits in that number is the number of significant digits that you'll use in the final product, the result. So there's only 4 significant digits here, and we covered this in earlier sections. You can either round it off manually. Now if you have a spreadsheet, you could probably cheat, and I'm just going to remove some decimal some numbers after the decimal point, and it automatically rounds. By the way, for this one, what I did is I went to cell C3, typed a plus, and then I took 9.345 and pressed the slash, and then moved the cursor to highlight 1.0567, and then I press return. And again, we get an unrounded figure, and you can format the cell so that it rounds it automatically for you. So now let's look at the answer that they provided. And their answer is 8.844 liters, which is reassuring because, pardon me, I made a mistake here in just rendering. You could see that the answer I got here is their answer. Again, I encourage using the computers to calculate things, and I'm so glad to feel vindicated. Mrs. O'Neill, who taught high school chemistry in 1977, was so insistent on using slide rules, and that's just ridiculous. She was one of the nastiest teachers I ever had. I'm still traumatized by that experience, because professionally, if you do this, I would expect a laboratory to want you to use computers so you don't mess up, and certainly don't use slide rules. So take that, Mrs. O'Neill. Anyway, let's move forward. Hopefully that was informative. So let's move forward. Beyond simple unit conversions, the factor label method can be used to solve more complex problems involving computations. Regardless of the details, the basic approach is the same. All the factors involved in the calculation must be appropriately oriented to ensure that their labels, units, will appropriately cancel and or combine to yield the desired unit in the result. As your study of chemistry continues, you will encounter many opportunities to apply this approach. Example 1.9. Computing quantities from measurement results in known mathematical relations. What is the density of common antifreeze in units of grams per milliliter? A 4.0 quart sample, 4.00 quart sample of the antifreeze weighs 9.26 pounds. Oh boy. So we're going to do a density calculation. So first we can calculate the density in pounds per quart. And let's see how they go about this. So strike what I just said. Let's just look at their solution. Since density equals mass divided by volume, we need to divide the mass in grams by the volume in milliliters. In general, the number of units of B equals the number of units of A times a unit conversion factor. I'm sorry, that does sound a little confusing. We'll work through it. Don't worry. The necessary conversion factors are given in table 1.6. 1 pound equals 4.5359 grams. 1 liter equals 1.0567 quarts. And 1 liter equals 1,000 milliliters. Mass may be converted from pounds to grams as follows. And they show that, let's see, I think they're actually providing this. 9.26 pounds is equal, 9.26 pounds, I'm sorry, let's see. Okay, 1 pound, I'm sorry, they provided it. 1 pound equals 453.59 grams. So to convert pounds to grams, you take 453.59 grams equals 1 pound. And so then So 9.26 pounds equals 4.20 times 10 to the third grams. I know this is a little confusing. Maybe as I work through an example, this will be a little clearer. But this is going to be multi-steps to get the units that are desired at the end. So now step 1, convert quarts to liters. So we convert the 4 quarts into liters at 3.78 liters. So let's just look back at the original problem, because they're throwing all these numbers. It's easy to lose track of what we're actually trying to do. So what we do is we convert the 4 quarts into liters, and we convert the pounds into liters. 4 quarts into 4 quarts into liters, and then we convert pounds into grams. Okay, now it's starting to make sense. So we're going to do this, what they're doing. So we convert the 4 quarts into liters, and that's going to be 3.78 liters. Now we need to convert liters to milliliters. So 1,000 milliliters is equal to 1 liter. And then we do a cancellation. So this is, I'm trying to think of how to make the visuals of this just a little clearer so we don't get overwhelmed. So anyway, that equals 3.78 times 10 to the third milliliters, and this is in scientific notation. Now you're seeing why the importance of the earlier sections, because if you didn't know how to do that, this would be really hard. So therefore, density, we just take, remember, density is the mass divided by the volume, and the mass is 4.2 times 10 to the third 4.2 times 10 to the third grams, and the volume is 3.78 times 10 to the third milliliters. Boy, that's a lot to keep track of. I mean, this is not, if we laid this out on a page, it might be a little easier to see what part fits where, because they just threw a whole lot of numbers at you. And if one could, maybe I could just shrink this down. If I could just shrink this down. Maybe we could see it a little bit better. Unless I had my pointer here. So the numerator here corresponds to a number all the way up here, and the denominator corresponds to a number here. So this number corresponds to this. So this is what's a little nicer. In the old days of having a blackboard, you could actually see everything laid out. Now alternatively, it says here, the calculation could be set up in a way that uses 3 unit conversion factors sequentially as follows. So if you want to try to do this all at once, it is certainly possible. You just throw the conversion factors one at a time. And by the way, this is more conventionally how it might be done, but it does help to be able to break it down in steps. So conventionally you might see it done this way, but to break it down in steps really doesn't hurt either. So I kind of like both approaches, because this is a little overwhelming here to just try to throw everything in there all at once. So to at least get partial credit, try to do it in pieces. And then as you get more versant in doing this, you can try doing it all at once. And unfortunately, sometimes you might have to do everything all at once. That is using all the conversion factors, listing them sequentially. So this will just take practice. When I've tutored chemistry, I'd say this is kind of, for the non-math savvy people, this can be challenging, and it just takes time and walking through it. So now, what is the volume? It's going to say check your learning. Now this time I'm going to try to actually do this. I'm going to show how I do all the steps by hand, and you can see it's a little tedious. So what is the volume in liters of 1,000 ounces, given that 1 liter equals 1.0567 quart and 1 quart equals 32 ounces exactly? What is the volume in liters of 1.000 ounces? Okay, there are various ways to do this. Let's set up some conversion factors. Now remember, the final volume we want in liters. So I'm going to bring my this was from an earlier slide. So 1.000 ounces equals, hang on, let me see this. I need to read this. Apologies here. What is the volume in liters of 1.00 ounces? So we want the result in liters. So 1 liter equals 1.0567 quarts. So 1 liter equals 1.0567 quarts. We already have that. And I'm just going to delete this conversion factor. And 1 quart equals 32 ounces. So 1 quart equals, let me just, 1 quart equals 32 ounces. One quart equals 32 ounces. Now let me see. I could totally mess this up here. So maybe that's how, well, that's actually how we learn sometimes. We have to do things, and if we make a mistake, we'll see how we made the mistake. So we have these conversion factors. We want the ounces to be converted to liters. And so remember that the idea is you put the unit you want to get rid of in the denominator. And so we want to get rid of the ounces in the denominator. Now, unfortunately, we don't have liters per ounces directly. We have to do it indirectly. So what we do is we take we have to have an intermediate step where we express it in quarts. So just remember, just start with by putting the unit you want to get rid of in the denominator, and then just put in the numerator whatever you have available. In this case, it's expressed in quarts. So 1 quart equals 32 ounces here. And let me just move this up a little bit so it's not quite so messy. So 1 quart is equal to, so just go with what you got. And then we do have the fact that 1 quart is equal to a liter. And we know we want to also get rid of the quarts. And this will just work out nicely. And again, just do it just by practice, you'll see this. So now let's try to set this up. And I'm just going through this in detail because this actually takes some practice. So I'm going to take this And what was it? We had 1.00 ounces. So we're going to take 1.000 ounces and we'll multiply it by a conversion factor. We'll multiply it by two conversion factors in the same equation. So let me make this a little bigger. I could have done this better. Apologies to the viewers. I don't know why it's giving me a hard time here. Okay, I had to actually pause the recording a little bit so I could create some diagrams to help illustrate this a little clearly. Hopefully it'll be clearer. So we have these conversion factors here, and now I'm just going to move forward and show how I use them. So these conversion factors that you see here in the colored boxes, all I'm going to do is just put them here. So we have, it's too bad I can't show two panes at once. This would be a little easier to see. But I took the conversion factors here and just multiplied them together. And let me show a little bit. There's some subtleties to this that are worth looking at. So the ounces will cancel like that, and then the quarts will cancel like that. And then when you put it through your calculator or your spreadsheet, and I'll again, just for the sake of trying to be helpful, I'll do the calculation here on my spreadsheet. So I'm going to go to cell D19 here. I'll type a plus and I'll say 1 divided by 1.0567. So all I do is I highlight the 1 here in column A, and then I press a slash, and then I highlight the next number, which is 1.0567 in the spreadsheet, and then press a slash, and then highlight the next number, which is 32. And we get that number. Now remember what I said, you can cheat a little bit and use the formatting feature to automatically generate the scientific notation if the result is to be in scientific notation. They chose to represent it in scientific notation. And there's some subtlety here with the significant figures, and there's supposed to be 4 significant figures according to the way they did it, and I'll explain that in a little bit. So I'm setting it for 4 significant figures, and you can see the answer I got, 2.956. 2.957 is the number I got here. Ooh, off by 1. Let me see. Let me undo that. 2.95. I think there's a mistake here in this answer. It should be 2.957. So something wasn't quite right. Let me double check my numbers. 1.0567, 32. Okay, I can't reconcile why they got 2.956. It should be 2.957. So let me redo the attribute. Now there's a subtlety here if one was keeping track of the significant figures. Notice this looks like only one significant figure, but remember this is a conversion factor, and to be a little bit more persnickety here, we could make this so that the significant figures are large. And we'll note that it says 1 quart is 32 ounces exactly. So this could be just like an infinite number of decimal places for the conversion factor. Now the final product will be constrained by the measurement that has the least number of significant figures. The measurement or the factor here that has the least number of significant figures. So in this case, it's saying 1.00 ounces. It's specifying we're trying to convert 1.00 ounces, 1.000 ounces, which is 4 significant figures. So the answer should be 4 significant figures. But again, the number I got when I put this in the calculator was 9.57. I mean 2.957. And so there's a discrepancy there that I can't reconcile. So this will happen, but I'm just going to say I think it's close enough. If that's the figure you get when you calculate it, then that's the figure I got. So maybe we're in agreement there. So let's just move forward. Let me just briefly see how many more examples we have. Oh boy, okay. We're going to have a lot more examples. I think I'm going to have to split this lecture into 2 parts just because this is already so long. So I'm going to split this lecture into 2 parts just because this is very involved. And I've often found that when I've tutored chemistry, this is not quick. So I'd like to thank you all for joining me for lecture 1.6, and I'm going to have another lecture on this that'll keep going with the examples. So thank you.